All right, what happens when we filter a noise sequence? Now we're looking at linear time invariant filters, our standard filters, and such filters can always be expressed in terms of a convolution, with the output being the impulse response of the filter convolved with in this case, our random sequence. So this works even if, say, we have an IIR filter that for which we would have an infinite length impulse response. We could always implement it in whatever way is most efficient and works best in a given situation, but from a theoretical point of view, we can express this in terms of the convolution equation. Here once again we have X as our random sequence, H will be the impulse response of the filter, and K is summed over minus infinity to infinity. That makes things a lot easier going forward. Well, now the question is, what happens to the statistics of X when we filter them? In other words, what does Y look like? We've just been talking about the power spectral density, and we often are concerned with what happens to frequencies. So we're going to start there and see what happens to the frequency content of a random signal when we filter it. So we'll define our autocorrelation function for Y in the normal way, the expected value of Y n plus m times Y of n. And then we get a long expression as we substitute in the convolution equation defining Y. So in this case, not much new, just a general application of the equation. I'm just talking basically so you can have a moment to look at it and digest what's going on here. It's the only main difference is that we have this x of k, h of n plus m instead of n because of the n plus m up above. So now we can rearrange this equation. It turns out in signal processing it seems like at least 90% of the proofs can be performed by changing the order of summation or integration and doing some change of variables. So we'll reuse those tricks several times here. First thing we want to do is note that the expectation is a linear operator, so it can float inside the summation. And not only that, the h's are deterministic, so they can escape the clutches of our expectation operator. And we're left with this product of h's with crazy indices and our x's. Well, the expectation of the product of x's doesn't look very usable yet, so the first thing we'll do is a little actually the second thing we'll do. First we'll note that that looks like an autocorrelation, and the autocorrelation, remember when we have two things in there, we find the difference. Normally we would have had n plus m and n, and so the difference would have been m, and that's what we've been using up above. But here we have k and l, so we get the autocorrelation of x evaluated at k minus l. Let's get rid of that k minus l, and so we will let introduce a new variable. I is equal to k minus l, and then we're going to need to take care of that l that appears elsewhere in the equation there in our h index, and so we will note that l is equal to k minus I. Since we are summing k and l over all infinity, this change of variables still sums I now and k over all infinity, so this works out just fine. After we've done this, we now have our autocorrelation function of x with an argument of I, and we can start turning our attention to these h's and see if we can make any sense of that. Okay, to simplify this, we'll do another change of variable, and this time we'll introduce j as being n minus k, which n minus k appears in both of these h expressions, so hopefully that'll be useful for us. And at the same time we can change the order of summation, one of our tricks again, and pull the autocorrelation function out. So we're left with now this little bit simpler function, a sum over h of j plus m, h of j plus I. From here, we could probably jump right to the end, but let's go ahead and put all the steps in so it's clear. And we're going to do that by making one last change of variable. We'll let p equal j plus I. And so now, when we're all done, maybe it doesn't look simpler to you, but it'll be really nice very soon. This second expression here, the sum over p, looks a lot like a convolution. Not quite, but very, very similar to a convolution. So what would it be if it was a convolution? It would have been h of m minus I minus p instead of p plus this. Or, in other words, this is going to end up being a convolution of h of negative n with h of n, except we've got our I minus m there instead. But let's, we're actually going to give this a name. We're going to call this function the deterministic autocorrelation of h. And in this case, it has an argument of m minus I. So that looks a lot like what we did when we approximated autocorrelation functions using sample statistics. One of the differences here is that if we were doing this with sample statistics, we would have divided out 1 over L, where L is the length of the sequence that we're working with, or the number of samples that we're working with. And in this case, we'll just define it this way. I just point this out because sometimes it's defined with a normalization factor and sometimes it's not. Often in signal processing, we use this definition, and we'll come back to that as we go. But the nice thing is now that we have this function that we've defined, and the way that we've defined it, we can write this whole expression as the autocorrelation of y is equal to the autocorrelation of x convolved with this deterministic filter autocorrelation. And so there we have this nice little expression that's, except for keeping track of the fact that we just took a complicated quantity and gave it a simple name, it's really a pretty straightforward expression. Okay, so why is this useful? This is really useful. Here's the magic. We know that if we take the Fourier transform, and there are two ways to write this. I'm just going to do this way for right now, and then we'll talk about it. Of the left side, that's equal to, on the right, we have our Fourier transforms, but here we have a convolution. And when we do a convolution, it turns into a product. So now we just have this product here, and we've got to figure out exactly what that looks like. Well, I'll just state right now, and then we can demonstrate it in a bit. This is going to be h e to the j omega, the Fourier transform of the impulse response, which is, of course, the frequency response of the system, squared. So there we are. When we filter a system, actually, and we have some names for this. When we filter a system, the Fourier transform of the autocorrelation of y is just equal to the power spectral density. So we get the power spectral density of y is equal to the power spectral density of x times the magnitude squared of the Fourier transform of our impulse response, or our frequency response. So whichever you like to remember, that's the way it goes. Okay, so back to what's going on with this, how we went from our autocorrelation, our deterministic autocorrelation function, to this Fourier transform squared. This particular expression here can also be written as phi HH and minus I. Oh, I'm sorry. I should have done that. Okay. Is equal to H of minus, hold on, just to make it simpler. If we let's put in something else, n instead of m minus I, just to keep the notation simpler. It's going to be h of minus n convolved with h of n, and the Fourier transform of that is going to be h conjugate e to the j omega times h e to the j omega, where the Fourier transform of h of minus n is going to be equal to the conjugate of the Fourier transform of h of n. And so that is, of course, equal to h e j omega magnitude squared. So that's where that comes from. Since p is a power, and the magnitude squared of h would be a power quantity, you can see that this is essentially, the power is essentially the same as if we'd taken the spectrum of x times the spectrum of the filter and then squared it, giving us the power spectrum of y. So let's go through one quick example, and that would be white noise. This is a great place to start because often you will want noise with a particular spectral quality. And white noise is completely uncorrelated. And so we're going to get that phi xx of m is just equal to sigma x squared delta m. And so the Fourier transform is just equal to sigma x squared. So if we're going to do some filtering here, we get PSD of y would be just equal to the magnitude squared of whatever filter we're operating with times sigma x squared. So if you want a particular power spectral density, you find you can start with white noise and unit variance, and all you need to do then is find a transfer function whose square gives you the power spectral density that you are looking for.